Hello, everyone. Sorry about the delay. Nice to see you all again. Okay, so that was the exam. Actually, I was very impressed. Good job, everyone. Uh, it looks like everyone was able to get a bunch of the questions right, which is the important thing. Let me just briefly put up the score distribution. So this is the score distribution. There's a large gap of 0 over here, which is very good. So somehow, the way I designed this exam, it was actually not designed for everyone to solve it. Whenever there's anyone who solves all the questions on the exam, I'm actually pretty impressed. That's just how these exams always are. And in particular, it's like, if you did this exam, the first 3 questions were supposed to be the ones that are like somewhat doable, where the somewhat becomes less somewhat as you get towards the 3rd question. Nothing here was really routine. And once you get to the 4th or the 5th question, they actually became really quite complicated. In fact, the 5th question, some of you saw that I posted onto my Facebook afterwards because I was kind of curious what other people in the world would think about it. And the 5th question was actually very interesting. So in any case, good job to everybody. If you didn't get all 5 questions, don't worry. If you did get all 5, I'm very surprised. And other than that, people might be curious, if I was curving this thing, what would I have done? If this was the only exam in the entire class, I think I sent it in the email already. If this was the only exam in the whole class, I would have said like around 35 or higher, that's like an A. Around like 27-ish and higher, that's around a B. Around like 20-ish, the cutoff for C would be like just under 20 points or something like that. And the fact that everyone got, at least one question solid, that's good. So people have the basic idea of this class. Okay, so that's the end of this recursion stuff. Any questions or anything about the exam? Or I guess in recitation they will go over the exam.
Dude, at this point, I'm just trying to get out, dude. I'm trying to just finish school. Dude, that's...
Cool. So that's okay. I get it. I think a lot of us are trying to just get everything done too. So totally cool. Totally cool. I think that many people can sympathize with that. And actually, some of what I'm working on right now is to hopefully make it so the world doesn't get as lousy as we keep going forward. But in any case, yeah, so that's the end of this particular piece. Let's go on to the next subject. The next subject is called graph theory. So graph theory, we're now drawing a line, and so for the next exam, everything's going to start from the graph theory onwards. Well, I mean, actually, I was anyway going to tell you about what I'm working on, because today is graph theory day 1, and what I've been working on for the last year is just graph theory, right? And in particular, I don't actually consider it an embarrassing moment, because I think that all that happened was that someone expressed the combined mood of everyone in the entire world. So I don't think that there's anything to be embarrassed about that at all. Rather, I think that's just why we need to do something about it, right? So what's a graph? A graph is something where you have a bunch of nodes. They're called vertices. So I've got a bunch of nodes. You can draw them as dots. And the nodes are called vertices. And oftentimes you'll see that I and many other people write them as VTXS's, and that's always very funny to me because the word vertices has no X in it. But anyway, that's how it works. So these are vertices. They're nodes in this nodes in this graph. And what happens is that you can connect some pairs of them. So it's just some kind of a diagram where you say some pairs of them are connected with each other. It could be that there are very lonely nodes as well, right? So we have all of these things that are connected with some kinds of edges. And the important thing is that we would say that this particular graph is exactly the same as if I wanted to draw another graph. I think it's the same as this one. I missed. Oops, let's go here. These are the same, right? Like what I've just done here is these are the same kind of a graph. We could actually have said, oh, I need to be clear. These mean something. Oh no, obviously they're not the same because I can't count. Okay, here we go. One more. It did look a little funny. Okay, so thank you everyone. One more vertex and one more edge. It's really funny because whenever you teach this subject, you're also sometimes you almost say the word, add one more vertice. But anyway, it's a vertex. So this is what happens. You got this thing. These are the same. And now the important thing is that the graphs usually represent something, right? So the graphs usually represent that there are some there's some relationships between people. There could be people. Like, there could be like Anna and Bob. I'm very lazy, so I'm trying to find short names. Carl, Dave. Ed. Oh, that's a nice short name. What's a nice short name starting with F? Frank. Okay, I just did it. So I have Anna, Bob, Carl, Dave, and Frank, and that particular graph, which is with these 5 people, is actually the same graph as, now what I have to do is I have to make sure that the labelings worked. I would have discovered that the number of vertices didn't match as I start labeling them. Right, I could say that was Anna, this was Bob, but now in order for them to be really the same graph, I need that Bob is directly adjacent to Ed. You already heard me use the word adjacent. This is almost like some vocabulary class at the same time. Adjacent just means that they're connected to each other, right? So they're adjacent along edges. That's actually what these are. So we have these connections, which is edges, and we also have some notion of adjacent. That's what we'll use. And the reason we always use the word these 2 vertices are adjacent is because the notion of these 2 vertices are connected. You could imagine that connected means like I could get from one of them to the other along some edges. So that's just why we don't usually use the word connected. We just say, or we don't use the word connected to describe adjacency. But now who's Ed adjacent to? Ed is adjacent to Dave. Oops, wrong color. Ed is adjacent to Dave. Dave is adjacent to Carl. And Carl is adjacent to Frank. And what I've just done here is I've just shown that when you have a graph, it's funny. The word graph sort of indicates some visual thing that you're looking at, except that graph doesn't require that you drew the graph in the same way. These are the same graph. They're actually the same graph. Same meaning it does not matter that I drew like what? Carl over here versus Ed over there. All that matters is that the same pattern of adjacency is there. So to have the same graph, all you care about is that all the things that were adjacent before are adjacent after. All the things that are adjacent after were adjacent before. That's the notion of a graph. Okay. Now, graphs are really important, actually. Can anyone think of any graphs in the world? Is there anything in the world that's a graph? Subway stations. Oh, yeah. So I was giving a talk to the Math for America group, a bunch of teachers. And, that was one of the examples that came. You could think of subway stations as forming a graph. And what I'll say is, in some sense, in the subway context, it does sort of matter where they are. But if you look at any subway map, you will notice that they take great artistic liberties in how they separate the thing out so that humans can read them. So in that sense, the graph of station connected to station connected to station, it's actually indeed not always the same as the geometrical one. But there are other notions of graphs too, which are like not even anywhere close to geometry. Anything else that might be a graph? You can feel free to type RH or just like, even if you want to unmute, that's cool. RH, Braden.
This one's a little bit silly, but I just remember from a game that a graph is described as the Wikipedia pages that link to other Wikipedia pages.
Oh, Wikipedia pages linking to other Wikipedia pages. So now that's an interesting kind of a graph. That would be the graph called All Roads End at Philosophy. This is this well-known thing that if you go to the Wikipedia and just like keep clicking on the very first thing on the Wikipedia, eventually you get to philosophy. But what you just gave about the Wikipedia graph, or more generally like the internet graph, right? It's like you have somehow like topic. What's a good topic? Platypuses. Platypus should not have an S. And then now the interesting thing is that the link has a link. What's a reasonable link from platypus? Obviously philosophy, right? Well, not really. Probably it goes to like, are platypuses mammals? I'm making this up. Are they? Okay, then I bet that mammal is one of them. Right? And like stuff like that. And the arrow means that it links to it. Actually, is it platypuses or is it platypi? Anyway, that's the only way to find out, by the way, is to check the Wikipedia page. Okay, which is now like circular logic. But anyway, so that's another graph. It's like the linkage graph, and you could imagine that maybe the mammal page, maybe it also has a link going back. That's possible too. You don't know, but mammals are probably going to go to animal, right, and so on. Okay, that's another graph. Any other graphs? Graphs are really important. I claim there's lots and lots of graphs. Other examples. Abby.
There was like an example from one called the like people's friends, like who you're friends with and who they're friends with.
Yep, you could also have like another one is like Facebook, right? Or whatever your favorite social media thing is. You have like people, and the linkage means that you are friends, which obviously is that's like one notion you could use. And in all of these social media things like Facebook, it's like symmetric relation. On Twitter, it would be a follow. I saw more ideas that were here. Sydney.
Oh, I was going to say the same thing, relationships with people.
Okay, relationships, friends, yeah. And Ben?
So say like maybe you can have all cities connected by air.
Oh yeah, you could have cities connected by air. Back when I used to fly, I would look at the magazine at the back of the plane and be like, oh, that's really cool. You can get from here to here. And you eventually notice that somehow there are some cities that are these hub cities that you can connect to other things. Yes, indeed. Actually, I used to have that graph sort of in my head because I used to go around a lot, and it would be the easiest way to figure out, like, how do you go from here to that spot? You think of whether they're connected or not by this graph. And then you'll actually find out very interesting things. Like, it turns out that the number of edges between India and China is remarkably small. I mean, I spent a lot of my time, like, kind of traveling around the world giving talks, and I found out that the graph of, like, where you can fly from and where you can fly to, like, somehow India, China, even though they each have, like, 1 billion people, the number of direct connections between Indian cities and Chinese cities is very low. But you just notice this if you look at the world as a graph theorist. Okay, so we've got all of these kinds of graphs. Oh, there's another hand that came up. Andrew.
I just thought of maybe this would be an interesting example. Maybe you could like consider like the predictive text when you're like texting someone like a graph of the
Oh.
possible directions that sentence could go.
Yes. Predictive text. And in fact, I think that's actually what they do. So I mean, you have some words like hi. And then probably the hi could go like, how are you, right? That might be like where this thing might go. But what else might you do? Like hi. What else do you possibly say after hi? Sup. I don't know. I'm just making up stuff, right? It's like whatever you type, whatever you typically type. It's just like it knows that there's this graph and it's trying to predictive text you. Okay? So that's another example. Actually, there's tons of these. I'll even share one that I didn't know about until I was a PhD student. But people even make graphs on things like proteins, where you will connect two things if there's a protein-protein interaction. And then you will try to use this to even try to deduce or discover interesting things in biology. In fact, you can use graphs to represent all kinds of things. It's interesting. People didn't raise this yet, but internet, or like the network, just the structure of computers connected to computers, that's also a graph. Okay, now why would anyone care about graphs? Well, there's lots of things that I've been doing these days that involve graphs, like in the real world. One of them is, here's a random tip. If you want to get stuff done and you need to talk to important and powerful people, there's a graph for that. That's the graph of who knows who, which is not the Facebook graph, and it's not quite the LinkedIn graph. It's like who knows who and trusts who. And I've spent like the last many years just like navigating this graph where you're like, how in the world can I get to that person? Is there any mapping of like who might be connected to them? And I'll just encourage, like if you think about the world in this way as a graph theorist, you will find yourself able to move closer and closer to talk to the people that you need to. There's another graph I'm going to talk about, just a very brief thing about what I have been doing for the last year. Some of you may know this because I've been talking about this at CMU too, but I and my team have accidentally invented a new way to fight disease. And the idea is very simple. In graph theoretic language, because that's the topic we have today, we have a simple idea of a graph. The graph is that the nodes are people, right? And so these nodes are people. Oh, I should call them vertices. Vertices are people. And an edge means that they spend a lot of time together, close together. They physically, let's call it physical contacts. Okay? So now you have all these people and you've got these physical contacts. That means that they spend time with each other. And let's just kind of like draw some randomish graph where I'm just connecting a bunch of things. Okay? It's nice that we're teaching graph theory, so I can just draw this where I just kind of draw something. Oh yeah, it doesn't have to be like, it can have weird loops like this too. Okay, let's just do this. So now I've got a very complicated looking graph. And what you have is, we've been thinking about people and edges, and we've been thinking about using this in the context of disease, like COVID. So for example, imagine that this person is sick, meaning that they have the disease. Well, I'm now going to use graphs to explain what we do. The way that humans have controlled disease for the last 3,000 years is when you have a sick person, you go and identify all of the people that they were directly around. Okay, identify all those people. And you attempt to remove all of these people. Let me do it this way. You attempt to remove all of these people from society against their will. That's like how you try to control a disease. Oh yeah, and the sick person too, right? So that's how you actually, somebody said it, LMAO, that's actually true, right? You've got to think about things. When you're a mathematician, you just distill it down to the way that unfortunately doesn't sound nice, but it's the truth. Like what's going on is that all these people have been told that you might be sick, and because you might be sick, you're a potential danger to everybody else, so please go away. And hopefully here at CMU and anyone else watching this on YouTube, hopefully you're sophisticated enough to not be really against your will, but you want to be a nice person and actually go and comply, right? So please do comply. But so that's how everyone's always controlled disease. And our idea was really simple. What we said is, hey, you know what? Suppose you're over here. Here, let's put this as you. That's you. What we said is, what if instead of just trying to remove people against their will, we tell everybody how far away. This is called the graph theoretic distance. Okay, so we're going to use the graph theoretic distance. Let's use blue for that. So there's a graph distance. And that's just equal to the number of steps you take in the shortest path, or the shortest number of steps to get from you to, well, shortest number of steps between two vertices. That's what the graph distance is. I'll call it the shortest number of edges. Let's be precise. Number of edges traversed. That was supposed to say traversed. So in this case, what's the graph theoretic distance? The graph distance between me and the sick person. Well, it's an abstract graph. I have to check. Can I go direct? It's like 1, 2, 3. That's one way. I could also go this way. 1, 2, 3, 4. The shortest one seems to be 3. I think is this. Oops. 1, 2, 3. Right? It's that the sick person is 3 from you. All right? So our idea was very simple. Instead of attempting to remove people against their will, just tell everybody what the graph distance is from every sick person. So new idea, it's very simple. Instead of this, you just change it to tell everyone their graph distance from sick people. Okay, why is this a big deal? It's simple. We just did something very simple, but this actually has something to do with incentives. See, the first one was trying to tell people you've already been around a sick person, so you should go away to protect everyone else from you. Ours was, well, it's beforehand. You're not actually sick. That person is quite far from you in this graph. But if we suddenly tell you, here's how far away it is, we suddenly made the first method that you could use it to avoid getting sick. Because if you can find out how far away a disease is as it's coming, before it gets to you, you can do something about it. And it took us quite a few months to realize this. It's just like the difference between, hey, you've already been around somebody, now you should go in quarantine. Change it to, it's coming, it's getting closer. Do you want to do something about it? That's a major difference in terms of the psychology. And the easiest way to explain why work on this still is because after we realized that, we said, well, hopefully COVID's going to go away. Thankfully, we have vaccines. This is going to be great. But what about the next disease? Like suppose there's some Ebola or something that starts, imagine someday it starts spreading by the air. Imagine there was some disastrous, awful disease that got, even young people sick. What would you want? Would you want to repeat this again, what we just had this year or last year? Or would you want to have a tool that can let you know if something's on its way, so that as you see it's coming on its way, you can actually do something, you can avoid, you can hide. And at that point, once you've made something that flips from telling you a Boolean true or false value, were you adjacent or not, flip it into tell you the graph theoretic distance, which is an integer. Once you flip that, you actually change all of the incentives. And suddenly it becomes a tool that people want to use to protect themselves. Anyway, so that's like a small thing. I'm not going to go deeper onto that. If you're curious, I do a lot of work on that. We can talk later, or you can look it up of like things that have been said about this. But the bottom line was it's just graph theory. It was simply saying if you have a graph, you can change what you're doing, and you can start using notions of like graph theoretic distance. Okay. Ooh, what's this? isn't this like NP hard? Oh, yes. Okay, so you're asking about some algorithmic aspects of like, wait a second, how can you actually pull this off? How will you know these distances? Actually, it is quite difficult. Fortunately, it's not what you call NP hard, because the distance between two vertices in a graph you can do in polynomial time. If you're curious about those aspects, I'm actually giving a guest lecture in 251 on Wednesday night. I didn't realize there would be some interest from this group, but if anyone here is curious, I'm going to be talking on Wednesday night. I can share it in the Canvas if anyone wants to. It's not part of this class, but 251 wanted me to go and give a guest talk about actually quite a lot of there's a lot of like interesting computer sciencey stuff that's behind all of this. But today we're just focusing on the graph theory, just getting used to the idea of graph theory. And why I'm trying to open with this is because a lot of times people say, why am I learning this subject? And well, what you just saw here is the tip of the iceberg of how looking at the whole world through a lens of graph theory could come up with a totally new approach to fight disease that never existed before, ever. Okay, but now if you want to do this, you have to also understand what kind of graphs you might come across. And that's actually what was a key part of making this innovation. It's understanding what kind of graphs you might see. So when you have graphs, you can have different kinds of graphs. And for example, I can draw some kinds of graphs that look like this. And you saw at the beginning I drew something that looked something like this, and I said, oh, I need to make it more complicated. So if I drew this, I'm just like randomly drawing something. This is a certain kind of a graph. Anyone see any interesting characteristics about this graph? Like, this is somehow special. Yeah, Advait. Yeah, there's like no cycles, right? So this particular graph here, there's like no cycles. And now this is letting me do some, like, again, graph theoretic vocabulary. What's a cycle? A cycle in a graph just means that you go around in some kind of a cycle. But a cycle means that you don't repeat any vertices. Okay? So a cycle means that you have some kind of a walk from vertex to vertex to vertex, never repeat until you get back to the start. And I'm saying never repeat, I'm sort of like ambiguous. Repeat what? Repeat anything. Never repeat anything. You can't repeat the same edge. You can't like walk on an edge and walk back. You can't repeat the same vertex either. And so this happens to have this interesting property that there's no cycles that go around. Okay? So that's true. And that actually is a very common type of object that you see. In fact, it's not only that there's no cycle. I'm going to say there's some other nice property about this thing that I've drawn, which is not only that there's no cycle, but there's something else about it. Anything else? Brayden.
There's a unique path between any two vertices.
Okay, so what you also said is that, and also, there's a unique path between any two vertices. That's also true. It's like if I wanted to go from some random vertex to some other random vertex, there's only one way to do that. Now, the interesting thing about math is that you can write down a bunch of properties, and sometimes you can conclude that some of those properties are automatic consequences of others. So what I'm going to say here is, you just said there is a unique path between any two vertices, and you've also said like, there's no cycles. But if I actually have both of these, oh, interesting. I'm actually thinking about this, and I'm like, this is actually a bit of a stronger characterization than the previous one, in the sense that, actually, by the way, if there's a unique path between two vertices, there's no way to make a cycle. So this is actually stronger than the previous one. And I say stronger because it also is telling me that it's connected. Connected. Remember, I used that word connected earlier, and I said I don't want to use the word connected for two vertices are connected, because there's a notion of connected, which is I can go through any path that I can go through a bunch of stuff and eventually get there. Okay? So I actually have to also add another interesting thing here. It's like the graph is connected. And the word connected just means that you can get from any vertex to any vertex, not necessarily uniquely, right? Connected means that, i.e., there exists a path between any two vertices. Okay? So that's true. And the interesting thing here is the yellow one is somehow stronger. It's somehow, there's a unique path between any two vertices. We're going to get through this. We're not going to do this part today, I think. However, I'm going to say that this particular type of graph has another name too. Advit. It's called a tree. So there's also something here, but this thing is also called a tree. Because it looks like one. It just looks like something you'd find on a tree. I mean, have you ever seen a tree with the branches where they kind of like merge together again? Actually, probably there exists some tree like that in the world. But I mean, most trees don't. And especially right now, because it's still winter, they really look like this because they don't have any leaves on them. But it's like, it looks like a tree. We'll talk a little bit more about like what's the relationship between tree and all of this later. But if you can see already, what we're finding out is we're writing down some properties. And the whole idea of graph theory is if I write down a bunch of properties, what other properties do I know? Or if I know two properties, do I know a third? Or like what's redundant? Okay, so this is where we're moving towards. But while I'm looking at this, I can also start to introduce some other things about properties of graphs. Or like if I'm staring at a graph, I can say, like imagine you were analyzing this, and this is like, hey, let's imagine these are the people of a relationship network, and they just happen to form a tree. Are there any interesting people in here? I'm basically saying like, these are vertices. Are there any interesting vertices? Are there any things I can say about vertices? We want to introduce some more lingo, which is also relevant if you're ever analyzing real graphs. I'm basically saying like, if you were analyzing this graph of relationships, and you were supposed to go and hunt around and be like, I want to talk to some people. Any particular aspects of vertices that could be interesting here? Chris? Okay, so now we're using this word connected, and that's why I want to use this like, no, it's okay. This has a technical term, which I haven't said yet today. It's called the degree. So the degree of a vertex is how many things are adjacent to it. Okay, so I'm going to write down some degrees. This is degree 2. Right? And if I go and look at some big one, oh, you said there's some of them degree 1. Okay, degree 1. And some big one. Counting is hard. I already failed on that earlier today. But that's degree 5. Right? And the degree of a vertex is equal to the number of other, well, I won't call it other, number of vertices adjacent to it. Now that drives me crazy, by the way, this definition of degree. It's because if you go and ask average people, like what's the degree of a vertex, they use things called LinkedIn. And LinkedIn has the first degree connections, the second degree connections, and the third degree connections. But those are graph distances. So actually what we were just doing earlier with this like COVID control or pandemic control, we were talking about graph distances. That's the shortest path that goes from you to the other vertex. LinkedIn calls those degrees. So what I call distance 1, LinkedIn calls degree 1. And what I call distance 2 from me, LinkedIn calls degree 2 from me. And the reason they do that is because there's a famous notion of the 6 degrees of Kevin Bacon, which says that somehow you... Actually, wait. 6 degrees of Kevin Bacon, is that about relationships with Kevin Bacon or co-starring with Kevin Bacon? I think it's relationships, right? Oh, it's co-starring. Okay, and people are like, what the heck is this? Yeah, the Bacon number. So there's this notion of the Bacon number, which is like, if you are Kevin Bacon, your Bacon number is 0. And if you star in a movie together with if you appear in a movie together with Kevin Bacon, then your Bacon number is 1. And if you didn't do that, but if you appeared in a movie with somebody who has a Bacon number of 1, then your Bacon number is 2, and so on. And somehow the 6 degrees of Kevin Bacon became a thing that people talked about. That's why degree is often used instead to describe like how how far you are. And indeed, Chris has said the Erdős number. That's actually, I think, what probably came first. Because Erdős number is like if you are Paul Erdős, who's a famous, interesting mathematician. If you look at his article, you'll find he's an interesting guy. But Erdős is 0. If you write a paper and you co-author with him, your Erdős number is 1. If you co-author with one of those, your Erdős number is 2, and so on. Okay, but these are degrees. Okay, so now with the degrees, actually these degrees are also relevant for other reasons. Actually, if you look at these trees, the trees have a lot of degree 1 vertices. What will come up soon, we'll use it for one of our theorems that we're going to prove early on, is that if you have a degree 1 vertex, that's actually often called a leaf. Now that's just because it sort of looks like maybe a leaf hanging off. Anyway, that's just what you'll see. But we'll see more of that later. But I'm emphasizing that the degrees are useful. And for example, if you were trying to analyze like the spread of a disease on a network, on a graph, you would actually probably be very scared of high degree vertices. And that takes us to the first, I guess, famous result in graph theory, which has to do with the degrees. Okay? So the challenge is Q, or challenge, try to draw a graph where the number of vertices is equal to 5 and the degree of each is 2. Let's start with that. Okay, is that possible? Can we draw a graph where it has 5 vertices and each of them has degree 2? Well, the answer is yes. There's actually a bunch of them. If I want to do such a thing, how to do it? Advait?
Draw a pentagon.
Okay, I'll draw a pentagon. I feel like this one. Oops, I lifted up my pen. Here. That's a reasonable pentagon, right? And all the degrees are 2. I know that you were thinking of a different pentagon, but this is the one I felt like drawing. Okay, so now, what's that? It's the same pentagon, of course, and I missed the vertex, so let me redraw the vertex. Okay, great. And then, of course, that makes me say, well, that was so easy. So do the same where all the degrees are equal to 3. If that was so easy, how do I do one with all the degrees equal to 3? Well, let's start, right? So you just try. Okay, how do I do this? If all the degrees are equal to 3, you start by, there's a 3 over there. And I need to make 3. Okay, so that was already 1, so 2, and then the 3. What's happening here? Oh yeah, I can make this 3. And I need one more that comes out of that thing. So okay, here, one more. So far, what do I have? I have 3. I have 3. I have 3. I have 3. And I have 2. That's really irritating. Clearly, I just didn't try hard enough. So I need to go and try again. Oh no, it didn't work. Now, actually, why I'm doing this is I'm trying to emphasize why graph theory proofs are interesting. Because actually, it turns out it's impossible. And maybe you already saw in concepts it's impossible. And so this is just like, you already know this, but I'm just going to do it as a review if you already know this. It's like, it's actually impossible. But a very bad proof of impossibility, you're not allowed to use proof by exhaustion called, I just tried and I got exhausted trying. That is not a proof. This is not practical. It's not practical to say I tried all of them. So that's actually why graph theory is interesting, because you can use theory to save yourself from having to do all of this. Braden, you were going to raise hand.
Well, we know that each edge is good to go between 2 different vertices, but if each of the 5 vertices has 3 degree, that's going to make for 15 total degree. It implies that we have 7.5 edges.
Yes, so this is something that I think is oftentimes in the concepts of math class. What you just said is that there's a theorem which is often called the Handshake Lemma. Okay, and the Handshake Lemma because it's about shaking hands somehow, and lemma because it's doesn't deserve to be called a theorem. It's too basic. But the idea is that actually, if I want to look at every edge adds 2 degree, right? Every edge contributes to me plus 1 degree and plus 1 degree on both of the endpoints. So every edge contributes me 2 total degree. Oh, let me write the theorem after I write the proof. Proof: every edge adds +2 total degree. Well, if that's the case, then that tells me that the 2 times the number of edges is the sum of the degrees. So let's write that down. So this says 2 times the number of edges is equal to the sum of the degrees. So that's very convenient. That's how we can immediately rule out the 3, 3, 3, 3, 3, because the sum of the degrees was 15. So this is impossible, since the sum of the degrees is equal to 3 times 5, which is equal to odd number, not 2 times the number of edges. Okay, so that dealt with this, and that's this handshake lemma. Okay, well, now some things that are also worth mentioning here. It's like sometimes people say, well, you know, but that's with these graphs where it looks nice, it looks kind of simple. You know, like, what if I decided to have weird graphs where you can decide that you can be multi-friends? You can be friends, like, I'm just like really, really, really good friends with this person. I want to draw 5 edges between them. You know, what if I did that? And what if I decided I just like myself? I want to be friends with myself too. You know, we can think of things like this. So now let me talk about things that are not so simple. Okay? And why I use the word simple is that there's a definition that a graph is simple if there are no 2 vertices with multiple edges. Multiple edges. That's actually what these are called. Multiple edges between same pair. Same pair of vertices. And obviously I program in C. But anyway, so, and you have this thing, no loops. These are called loops. All right, so there's no loops. Okay, so that's called simple graphs. And in fact, if you think about it, a lot of the graphs that you might think about are simple. They don't have these like multiple edges, they don't have these loops. And that's convenient. And in fact, for basically this entire class, if I use the word graph, assume that all the graphs are simple, unless otherwise specified. So in this class, assume all graphs are simple unless otherwise specified. I'm writing that down as a phrase here just so that it's very clear. I don't want to, I mean, I might even give you exam problems where I forgot to write the word simple. So it's just like, yes, please, just think of it as simple, because that's like many of the interesting graphs in the world. Okay. But now, unless otherwise specified, let me now otherwise specify, because I want to explain what you would call a degree if you have that kind of a situation, in case you ever saw something like that in another class. But in not simple graphs, what you would do is, if you were counting a degree, what might make sense? Let's think about this. Suppose if you have a not simple graph, and like these 2 people are really, really good friends with each other. I just made that up. Some simple thing. No, I mean some easy thing, but this is a non-simple graph. What would make sense for the degrees? What do you think? What should we call these degrees? I just drew this random picture. It has a triple edge and it has a 1. Actually, this probably deserves to belong in some kind of chemistry textbook. This reminds me of like organic chemistry or something. But anyway, what would the degrees be? What would be reasonable ways to define the degrees? And a good definition is one that has like nice generalizations or feels right with all of the proofs we already have. There's not really a wrong answer. It's more of I'm trying to motivate. I'm trying to motivate how all of these definitions actually make sense and are useful. What are good ways to assign degrees? Jack.
I guess my first thought is it's still the number of edges going in, even if it's a multiple.
Okay. Yes.
It's because I was thinking in the last book you said every edge adds 2 to the sum, right? And I still want that.
Yes, that's the right way to think. It's like, I want as many things that were true before to still be true now. That's your goal, right? In math, we want things as consistent as possible. That's why 0 factorial is 1, right? You make it so that you can have as many things as possible still retain true. So you're like, I want that if there's 3 of these edge-ish things coming off, like handshakes, it's like, come on, they just shook hands 3 times. That's what this means, right? So the degree is just how many things are coming out. Degree 4 and degree 1. And what you get from this is the same handshake lemma is still true, right? So in the not so simple, this thing here is like still okay with handshake lemma. Handshake lemma still okay. And now the one that I want to put up that is like interesting, not that this wasn't interesting, but there's one which is like, what do I do with the loop? Here, I'll do that. It's got 2 loops and, you know, whatever, that. What are reasonable degrees here? What do you think? Anyone want to hazard a suggestion? Advait?
The one with the loop can have degree 5.
Uh-huh.
And then the rest can be like how they were before.
Yeah, how it was before. And why did you want 5? I mean, why did you want 5 instead of like, it has 3 or something?
I still want each edge to contribute 2 to the degree.
Yes, and it's okay because like somehow you can shake hands with yourself too. And if you shake hands with yourself, you just made +1 +1, right? So the important thing is that I'm just pointing out that if you have a loop, you actually count the loop as +2, right? The loop is +2 because it has 2 ends coming off of it. But it's okay. It's like the handshake lemma is still okay in both of these, which was the entire point. Let me erase this arrow and make this more clear. It's still okay in both of these. Okay, so that's this notion of like handshake lemmas and the degrees. Okay. So now that we have all of this is like notions of simple graphs. Simple graphs are the ones that don't have these things. Now let's continue thinking about our world of interesting kinds of graphs that you might be able to stare at. Another kind of interesting graph that you'll stare at is something that looks like this. Maybe I'll just draw 4 vertices like that. That's one of them. Here's another one. I'll draw a pentagon on the outside and then some kind of a star inside. Any interesting properties of what I've just drawn here? As we're thinking about graphs, it's like, here's another kind of graph that you might see. Lots of people. Nancy. Between any 2 vertices have 1 edge. And these are really important graphs, actually. These have a name. These are called complete graphs. So these are called complete graphs. And we actually have ways of writing them down. Complete starts with a K, as you know. Actually, it doesn't, but somehow it's always a K. Complete is with a K, and this complete graph is K5. I used to think that it might be because in German, complete starts with a K, but somebody told me that there's a better word for complete graph in German that starts with a V, and so that there goes the theory. But anyway, it's K. And the reason why K is convenient is because there's also another kind of a graph where we want to use the C. There's some other kinds of graphs that you might see, and these kinds of graphs might be, I'm just going to draw something. That's another graph. Here's another graph. These are C for cycle. Yes. I mean, this is another very important kind of graph. We've already seen the word cycle appear. Cycle appeared when we were talking about these trees. So it's going to be important to talk about cycles. And these things here are called cycles. Let's use a different color. These are called cycles. And this thing is called C, how do you count? C6. And this is called C4. Okay? Fun fact, C4 can be drawn in a funny way. I found out at some point in my life that this is also C4. Even though it looks very different. Actually, this one is a type of shape that we're going to see in later in this class. This is actually also called a complete graph in some sense, but it's it's a complete graph with two parts, where I have like all the stuff on the left and all the stuff on the right, and everything on the left is kind of adjacent to everything on the right. So it's interesting that C4 does double duty also as this. Ah, yes, somebody already said it's like K22 or whatever it's called. Well, since that already came up, let's talk about that. That's another kind of a thing that might appear. Another thing that might appear, and oh yeah, by the way, I'll never give you a test called like name all of these graphs. That's not the point at all. I'm just trying to explain to you like here are the kinds of animals that we might see in the zoo. That's actually how we think of it. Like graphs is the graph theory, all these funny animals. And so you might have another kind of a graph where now we're going to be a little bit more abstract. It's like called this thing like there's S vertices here and there's T vertices there. And I connected everything, I made everything adjacent in between. Okay, so what this thing is like all pairs between are adjacent. Oops. Between are adjacent, and that happens to be called complete S comma T. It's like somehow it's very complete, but it has two parts. There's S things over here and T things over there. And those also actually come up quite often when you're thinking about graphs. No edges within S and T, correct. And there's like no edges inside each part. S or T. Okay, well, we have about 3 minutes left, and I'll use the three. This generalizes to more than two parts. You can. We're not going to go too deep into that here. Like you could imagine, you have a bunch of different blobs, and you start connecting all things between, making adjacent all things between them. If you like this subject, by the way, there's an entire class called Graph Theory, class 484. Sometimes it's taught by, John Mackey, Wes Pegden, really interesting people. Actually, everyone who teaches the class is really interesting. But there's like this entire region of math called graph theory, and they do all these analyses. Here in this class, we're sort of giving an overview of like some of the key facts in it and why it's interesting. But now I'll close today's class by just saying, well, why do I care about knowing all these animals? It's because actually it matters what the graph looks like if you're going to do something applied. For example, if I'm doing something with the infections and like people using an app, that actually is where some of our ideas came from. What should that look like? What do you think the graph of people's actual physical interactions looks like? This is a modeling question. And in fact, right now, we're also working with epidemiologists who are making models to estimate this. This is actually, there's no good answer to this, by the way. It's like, if you were trying to make a graph to look sort of like people who spend time with people, what is it? It's not a complete graph. It's not a tree. It's not a cycle. In fact, it just shows you that these animals in the zoo are not really good enough to describe all the graphs. Advait, you have an RH question. What's your suggestion?
Well, could you do it like this? Just make a bunch of blobs with vertices in them. You put a bunch of connections within each blob and not many connections between the blobs.
So here are some blobs, okay? We got some blobs, and they're like some edges in between. And you're like, it's pretty dense inside them, okay? All right, I'm going to add one more piece, which is important. They overlap. Is that okay?
Okay.
That's a very important detail. It's like they overlap. They look like this. So what we just did is we basically superimposed a bunch of very dense graphs. It's almost like we were talking about complete graphs before. That's like where everything is there. And here we have like some pretty dense graphs. It's like close to complete or something like that. We could imagine that you superimpose a bunch of very dense graphs. Okay? And then maybe you could say that's sort of like the human interaction, physical interaction network. Okay? And now there's a reason why this was important. It's because, for example, for the things that we're doing, if you happen to model it this way, then it turns out that if you have any vertex, we're talking about distances now, if you have any two vertices, and you're measuring the distance between those two vertices, even if a lot of people aren't using your app, meaning that the vertices are missing somehow, your estimate of the distance is about right, or not far off. Does that make sense? This is actually a pretty intense observation. It's that if the way that your graph is laid out is such that you have a lot of these overlapping blobs, which could be like your floor of the dorm or a class that you're attending or your social group of friends, but because it overlaps with this other social group of friends, there's a lot of overlap. What this means is that estimates of the distance, the graph distance between pairs of vertices are robust against vertices disappearing from the graph. Did that intuition sort of make sense? Whereas if you have a tree, by the way, if you have a tree, well, if I have this vertex and that vertex, and some people in the middle decide randomly not to use the app, what's the distance between them? Infinity. It broke. This is the unique path. Does that sort of make sense? So I'm just explaining, like that's what we do in graph theory. The reason why it's useful to know about all these different kinds of graphs and to have some level of intuition about them is because then you also are able to make some theoretical reasoning of, suppose I'm going to do something and I have an actual graph. What happens? How robust is it against not perfect behavior or not perfect usage? Anyway, so that's what I actually do. In fact, the area of research that I work in overlaps with this idea of random graphs. I'm actually a random graph researcher. And what we do there is we kind of think about all kinds of things of, well, what if I have this real graph and I lose half of the edges or I lose half of the vertices or in some random way. But hopefully this gave some indication of why it is useful to start thinking about graphs and to maybe start thinking about what kinds of graphs there might be. And we're going to spend the rest of this semester just thinking about all kinds of interesting properties of graphs. So that's it. That's it. Yep. I'll close out the